Hello, welcome back to Chemical Engineering with Jessica. So today we're going to be learning about the most important topic in chemical engineering, which is material and mass balances. Woohoo! What could be more fun? These are based on the law of conservation of mass, which states that mass can neither be created nor destroyed. We are going to make a material balance out of that, based on you can't have material appear from nowhere, and you can't destroy material, so it can't go away. If something goes into a process, it has to come out. Now, it might come out in a different form. We can have reactions that take place, but the mass itself will still be there. So our general material balance, which is applicable for everything, states that in minus out plus generation minus consumption is equal to accumulation. For a system at steady state, we can assume that our accumulation is equal to 0, because steady state is defined as there's no change in anything. There's no change in the system. It's operating at constant flow rates. It's operating at constant temperature, pressure, all of the above. As such, there's no change in our accumulation either. Mass balances can be done on the overall system. You just basically put a box over the whole process. There's a lot of stuff inside the box, but we just ignore it. You just say what's coming into the system, what's going out of the system. And then you can calculate it based on that. You can also calculate a material balance or mass balance for an individual processing unit. So say like a reactor or a distillation column, a heater, whatever. So to break it down more, you can balance an individual species that is flowing through your overall system or process unit too. And so the combination of all these will help you to solve for any unknowns in the system. Let's solve out a problem. All right, so this problem states that 1,000 kilograms per hour of a 50 weight percent benzene toluene mixture enters a distillation unit. The top stream flow rate of benzene is 465 kilograms of benzene per hour, and the bottom stream toluene flow rate is 470 kilograms of toluene per hour. Determine the unknown component flow rates in the top and bottom streams. Okay, so let's break that down a little bit. First thing we always do is we draw a picture. So this is our picture. 1,000 kilograms per hour of 50 weight percent benzene is entering the system. And the 50 weight percent benzene defines out of all of the mass that's in the entering flow stream, 50% of that comes from benzene. We only have benzene and toluene in the system, we know that. And so that means the other 50% is toluene. And we'll deal with more with that later. So our top stream, we have 465 kilograms of benzene flowing per hour and an unknown amount of toluene. Then in our bottom stream, we have 470 kilograms of toluene per hour and an unknown amount of benzene. So next, we're going to set up our overall mass balance. So we're going to use our equation, in minus out plus reaction, where we have no reaction going on here between benzene and toluene, so I just combine the generation and consumption terms into just one general reaction term, which is equal to 0 in this case. That equals accumulation, and for this situation we are going to assume that it's operating at steady state, which means that our accumulation is equal to 0. So basically we just have in minus out is equal to 0. Using that, we have 1,000 kilograms per hour is equal to 465 plus XB, kilograms of benzene per hour, plus XA plus 470 kilograms of toluene per hour. All right, so we have two unknowns and one equation, so we need more. So let's go to individual species. So first we're going to do the benzene mass balance. We have in minus out plus reaction is equal to accumulation, which we already determined is equal to 0. We have 50 weight percent benzene. So the way we convert from our weight percent of benzene to the actual flow rate of benzene is by multiplying the overall flow rate, which is 1,000 kilograms per hour, by our weight or mass fraction, which is 0.5. That's going to give us 500 kilograms of benzene per hour flowing into this distillation column. Very fun and exciting. So using our 500 kilograms of benzene per hour, we're going to put that into our equation as our in. So we have 500 kilograms of benzene per hour minus 465 kilograms of benzene per hour minus xb kilograms of benzene per hour is equal to 0. Rearrange it to solve for xb, and we're going to get that xb is equal to 35 kilograms of benzene per hour. Okay, finally, we're going to complete this with our toluene mass balance. We're going to do the exact same thing. In minus out plus reaction is equal to accumulation, which is equal to 0 since we said it's steady state. So the way to find the toluene flow rate is using 1 minus the mass fraction of benzene, because we only have benzene and toluene entering the system. We're going to multiply 1,000 kilograms per hour times 1 minus 0.5, which is still 0.5. That's going to equal 500 kilograms of toluene per hour. So we're going to put that into our toluene mass balance, and it's going to be 500 kilograms of toluene per hour minus 470 kilograms of toluene per hour minus XA kilograms of toluene per hour is equal to 0. We're going to rearrange to solve for XA, and we're going to get that XA is equal to 30 kilograms of toluene per hour. All right, so now we know all our unknowns. So just to go ahead and check, we're going to plug all our stuff back into the overall mass balance. Our top stream total mass is 495 kilograms per hour, and our bottom stream total mass is 505 kilograms per hour. Using our overall material balance, 1,000 kilograms per hour in, minus 495 kilograms per hour out in the top stream, minus 505 kilograms per hour out in the bottom stream is equal to 0. Our mass balance balances, and all is well with the world. So that's all for today. I'll go more in depth with this in the next video, but this is the basis of mass balances. So I hope you'll have a great day, have fun learning this, and remember that the only way to true knowledge is to know the one who created you and loved you enough to die for you. Bye!